The final orbital we're going to talk about are the f orbitals. You can't really draw them. They're incredibly complex shapes, and they're even higher energy than d, very high energy. So that's really you have to know about them. They're very complex shapes that we usually tend not to draw, and they have high energy. So next up is the magnetic quantum number, and that's denoted by m subscript l, not ml, m subscript l, the little l. And they are from anywhere from the negative L value that we talked about before, the angular momentum number, to L. That's like the range of them that they can be within. And all they really show is the orientation of the orbital. Like as we said before, the p orbitals can be drawn on the x or y or z axes. This is what tells you what axes they will be drawn on. Next up is the spin quantum number, denoted by m subscript s. And this is like probably the easiest quantum number you have to know. All it shows is just going to show there's two electrons that can be in any orbital, and they either have to have a spin of +1/2 or -1/2. Doesn't matter if it's like a p or s orbital or like a p orbital or any of the other ones. You can pick whatever electron spin you want. So if you have one electron in the s orbital, you can make it -1/2. You can make it +1/2. Whatever you want, whatever floats your boat, doesn't really matter. Another important thing you should know is the Pauli exclusion principle, and what that says is that no two atoms can be exactly alike. The closest they can come together is having different spins. So what this means is that the four quantum numbers can be similar, but again, the spins have to be different. Next up is electron screening and electron shielding. Now, as you know, the nucleus of the atom is positively charged, and the electrons are negatively charged. What this means is that they are naturally attracted to each other. However, other electrons are negatively charged, and they want to repel each other. Basically, what this means is that if there weren't any other electrons present, if there was only one, it would be much more tightly bound to the nucleus than if there were multiple electrons present repelling them. Now we're going to talk about the Aufbau principle. AUF-BAU principle. All this shows is that for every proton you add, you also add an electron. So as you move across the periods of the periodic table, you're adding protons because you're making a new element. You also have to add one new electron to the orbitals to account for that. Next up, we're going to talk about Hund's rule. Hund's rule basically says that the most stable form an atom or electrons can take is when they have the most number of unpaired electrons in the orbital. So, like in this hypothetical d orbital, you can tell it's a d orbital because it has 5 boxes. Let's say we have 5 electrons, right? You put 2 here, 1 here, 1 here, 1 here, and then this box is blank. As opposed to this one, where you have 1 here, 1 here, 1 here, 1 here, 1 here, and then there's no blank boxes. Hund's rule would tell you that while you could draw it this way, this is incorrect. This is the correct way because this is how it would naturally form, because as you know, things want to be stable and they're going to go to this orientation before they go to that one. However, if you were to start adding more electrons, then they would start pairing up. So then they would do this, and then this, and then eventually they would complete the orbital set, and you'd have all your boxes filled up by those 2 electrons. Next, I'm going to talk about periodic trends. You'll notice as you go across periods on the periodic table, the size of the atomic radius of atoms decreases because you're adding more protons, which will have a greater pull on the electrons and pull the shape of the entire atomic radius in closer to it and compact it more. However, when you go down groups, down the periodic table, the size of the atomic radius increases because you're adding more and more principal energy levels, like on that Bohr model, more and more of those rings, and that causes the atomic radius to increase. Now, using the same idea of the differing atomic radiuses, or radii, you can look at the ionization energy and also see a trend there. So, as I said before, when you go across a period, the radius of the atoms will be decreasing. What this does is it causes the ionization energy of these atoms to be higher because there's a greater pull by the nucleus on that electrons, and it's harder the nucleus wants those electrons more, so it's going to be harder to pull those electrons out and ionize them. Again, as you go down the group cell, as you go down the group cell, because there's more principal energy levels, they're going to shield that pull of the nucleus, that positive pull of the nucleus, and because of that, the outer valence electrons are going to be much easier to pull because they're not feeling the same attractive force from the nucleus. Next up, electron affinity. It's basically the opposite of ionization energy, how much something wants an electron, as opposed to how easy it is to take the electron out. And it's the same pattern though as you look at the periodic table as ionization energy. As you go across a period, the electron affinity goes up, and as you go down a group, the electron affinity goes down. So for example, chlorine has a much higher electron affinity than, say, carbon, because chlorine is located farther to the right on the periodic table, and it only takes one electron to complete its shell, and therefore it really wants that one extra electron. Carbon, it still takes 4 more electrons to complete its shell, and because of that, it does not have a higher electron affinity than chlorine does. And then as you go down the group, it's harder for the nucleus to pull those electrons, again, because there's all those principal energy levels that are blocking its pull, and therefore the electron affinity is lower as you go down the group.
You want it?
So I've been talking about atomic radius, but in case you don't know, the way you find atomic radius is by taking 2 atoms that are right next to each other and dividing the distance between the nucleus of those, or the nuclei of those 2 atoms by 2. You do this because if you look, one radius is right here, and one is right here. So the distance between both of them is 2r. Now if you divide that by 2, 2r divided by 2 is r. And that's how you find the atomic radius of one of these atoms. Okay, finally we're going to talk about alkali, or
Alkali.
I'm thinking, I got it mixed up. Finally, we're going to talk about alkali or metals.
No, alkali.
Alkali? I thought it was alkali.
No, it's alkali.
Okay.
Or we have
Say alkali or alkali.
Alkali. Finally, we're going to talk about alkali metals, and did I do it right?
No, that was right.
No. Finally, we're going to talk about alkali metals, and basically what these are, they're the first group on the left of the periodic table, and they easily oxidize. They only have 1 electron that they want to get rid of because that will make them the most stable. So they easily get rid of that 1 electron, and they react a lot with halogens like chlorine to form salt. So as you know, NaCl, your common table salt. This right here would be the alkali metal, and this would be the halogen. This one would give up the 1 electron, +1. This one would gain it, and they both become stable in doing this. That's just an example of them forming a salt. And they also have very large hydration energies, for what it's worth. And that's it.